Hello and welcome to this video on torque or moment of a force. Now, the sequence of this video is this. We need to understand basically what is torque or what is meant by the moment of a force. Now, torque and moment of a force are actually equivalent and they may be used interchangeably in physics. Now, first of all, we'll have a conceptual understanding of torque. Now, if you really want to understand torque, you also need to know what is meant by the line of action of a force. So later on, you'll understand what is meant by the line of action of a force. And there are two important definitions that you need to know. One is lever arm. What is meant by lever arm? And then you also need to know what is meant by the lever arm distance. In this video, you'll also learn whether we can calculate torque and how we can calculate torque. And finally, we will look at, can we add torques? Like how we add forces. Torque, or the moment of a force, or sometimes people simply call it as moment, is given the Greek character tau, or the Greek letter tau. Now, torque, or moment, is the tendency of a force to rotate an object. And when an object rotates, there is a stationary point on that object. This stationary point is known as the axis, or sometimes known as the pivot point. So when an object rotates, it rotates about a pivot point. Now, this video shows you an infant who's trying to use a wrench to unlock a socket. As you can see, as it tries to turn the wrench, or with the help of his dad, I guess, he inserts it into the socket and then he uses his hand to turn the socket. When he uses his hand, he's basically applying a force, and this force creates a turning effect on the wrench. Now, mathematically, torque is given by F times R. Okay? Now, tau in this equation here, this Greek letter tau represents the torque. R represents the lever arm distance or the moment arm distance. And in SI units, the moment arm distance has the units of meters. F represents force. And in SI units, force is given as newtons. What are the units of torque? I'm sure you need to understand what is meant by this lever arm distance. Now, before we learn about the lever arm distance, it's a good idea to look at what is meant by the term lever arm, first of all. Now, the lever arm is the shortest vector that you can draw from the pivot point to the line of action of the force. Okay, and the lever arm distance is the length of the lever arm. Now, I will use the example in the next slide to illustrate what is meant by lever arm distance, and the line of action of a force. I'll be using this example to illustrate what is meant by line of action of a force, what is meant by lever arm, and what is meant by lever arm distance. Now, what we have here is a force F, which is acted on a wrench, and the force F has an angle of phi with respect to the body of the wrench. Obviously, when you apply a force on an object, we may cause a turning effect, or we may produce a turning effect. So as a result, we may produce a moment or a torque. Now, this vector of force F is in this particular direction. If we were to extend this vector below the tail with some dashed lines, and even above the head with some dashed lines, we get something known as the line of action of F. So basically, this dashed lines, which extends the vectors in both directions, okay, is known as the line of action of the force. What about lever arm? Now, the lever arm is the shortest vector that you can draw from the pivot point, which I've pointed out in green here, to the line of action. Now, from geometry, you should be able to realize that the shortest vector that we can draw from a point to any line is a vector or a line that is perpendicular to that line. So basically what I'm doing is I'm drawing a line that is perpendicular to this line of action that joins the pivot with this line of action. So this vector is known as your lever arm. So what is the lever arm distance? So this lever arm distance is nothing but the length of the lever arm. So the magnitude of the lever arm, the length of the lever arm, length of the lever arm will actually give you the lever arm distance. Now, if I say that the length of the wrench or the distance of the pivot to the point of contact of the force is L, capital L, then let us say that R is the lever arm distance. You can or should be able to express R in terms of L and phi. So R is equivalent to L sine phi as illustrated in this particular example. But what is the moment or the torque that is produced by this F? Now, in this slide, we will look at an alternative approach to the problem in the last two slides. Okay, now what we have is a resolution of F. So we resolve F into two components or two mutually perpendicular components. One, the vertical component F sine phi, and the other is the horizontal component or F cos phi. Now, when we have a situation like this, the torque or the moment that is produced will only depend on the component of the force that is perpendicular to the object. So this F sine theta is actually perpendicular to wrench. So it is the only force that produces a moment or a torque. The moment produced by this force will be equal to 0. Now, why am I saying there are two moments is because when we resolve a force into its components, we effectively get two forces. So when we get two forces, we can actually get two moments. Now, in this slide, we will understand a little bit more about the nature of torque or moment. Now, torque or moment is a vector quantity. So it's a vector quantity, not a scalar quantity. And because it's a vector quantity, it will have both magnitude and direction. However, the unique thing about torques or moments is that because you rotate an object, and the only possible direction you can rotate is either clockwise or anti-clockwise, or sometimes people call it as counterclockwise. So the direction of a moment or a torque is either clockwise or anti-clockwise. Point to ponder. Why do we place doorknobs furthest away from the hinge as possible? So if you don't know, the hinge of the door is the point or the axis about which you rotate the door when you close or open the door. So why do we place the doorknob furthest away from the hinge? If you really understand torque or moments, you should be able to answer this question in a jiff. Now, let's move on to something a little bit more complex. What happens if there are two forces that are exerted on an object that produce a turning effect? Or in other words, you have two torques or moments being produced. How do we add these moments, or can we add the moments? Let's look at this simple example. We have a boy sitting on the right side of a seesaw. So by basically sitting on the seesaw, he's exerting his weight onto the seesaw. And we have probably his little sister or his girlfriend sitting on the other side of the seesaw. She will exert her weight onto the seesaw plank. Now, as you should be familiar with seesaws, there will be this point in the middle which is stationary, and we call it the pivot, or you will be more comfortable with this term, fulcrum. Probably some of you would have heard or read about this fulcrum. Now let's look at the boy first. Now the boy is exerting his weight onto the seesaw plank. Think, which direction will the boy tend to rotate the plank? As you should be able to figure out, the boy, from our view, the boy will try to rotate the plank in a clockwise direction. Now, if you cannot imagine this, imagine you hold a pen and then you exert a force onto the right side of the pen. So you hold the pen at the middle, okay, your two fingers holding a pen. You exert a force onto the right side of your pen. See, which direction does your pen rotate? Does it rotate clockwise or does it rotate anti-clockwise? Now let's look at the girl. The girl exerts a force or a weight onto the left side of the pivot. So this will produce an anti-clockwise moment. Now, how do we actually add moments? We will see in the next slide. Now, similar to adding forces, torques can be added to find the net torque. Okay, the net torque is the resultant torque by adding all the torques that act on the object as vectors. Now, the unique thing about torques or moments is that they have only two directions. You either can have a counterclockwise torque or you can have a clockwise torque. So the assignment, whether you want to assign positive to counterclockwise and negative to clockwise, is entirely up to you. You could also say counterclockwise torques are positive, clockwise torques are negative, or you can say counterclockwise torques are negative while clockwise torques are positive. The reason is both directions, clockwise and counterclockwise, are opposite. I'm using this slide and the example on the slide to illustrate how we can actually find the net torque of a situation like this. Now, the girl sits on the left side of the pivot. As you should know, the pivot is here. Okay, there are weights given. The girl has a weight of 500 newtons. The boy has a weight of 800 newtons. And then you have this normal reaction force. Where does the normal reaction come from? Okay, where does the normal reaction force come from? Basically, when the seesaw is resting on the pivot will exert a normal reaction force onto the seesaw. So this normal reaction force, or sometimes called just the normal force, is on seesaw by pivot. So this is the force that the pivot exerts on the seesaw. So as you can see, we're listing all the forces that are acting on the seesaw. The boy and the girl's weights, they are sitting on the seesaw, so they exert their weights onto the seesaw. And then you have this pivot, which the seesaw is resting on, exerting a normal reaction force. Now, in this example, we are assuming CCW rotation to be positive. What is CCW? CCW stands for counterclockwise, counter or anti-clockwise. Okay, because when an object rotates, there are only two possible rotation directions. One is counterclockwise and the other is clockwise. Now, the boy produces a clockwise rotation. The boy produces a clockwise rotation. Now, if you don't understand why he produces a clockwise rotation, what you can do is you hold a pen. You hold the pen at the middle. Okay, so use two fingers to hold a pen, and your two fingers grips the pen at the middle. Apply a force using your other hand, using one of the fingers of the other hand, on the right side of the pivot, which direction does your pen rotate? What happens if you exert a force on the left side of the pivot? Which direction does the pen rotate? So as you should be able to see now, the girl is sitting to the left of the pivot, so she will produce a counterclockwise rotation. Now, the moment she produces, or the torque she produces, is this. It will be 500 newtons multiplied by 4 meters. That will be the moment that the weight of the girl produces. Now, the weight of the boy will produce a moment or a torque about the pivot of 800 newtons multiplied by 2. So if you do a simple arithmetic, you'll be able to see that you'll get positive 400 Newton meters. Now, positive means it's counterclockwise. So basically, the net torque is 400 Newton meters counterclockwise. This tells you that the seesaw will rotate counterclockwise. Okay, since the net moment or the net torque is positive 400 Newton meters counterclockwise, the object will also rotate counterclockwise. I hope we had fun. I hope we had learned a few things. See you soon.